So instead of generating an electromotive force, what if we wanted to generate electricity? So we'll get into the idea of an electric generator in this lecture. I'll skip a little bit here just in the interest of time. But basically an electric generator uses energy of other types like thermal, gravitational, or kinetic, in most cases kinetic, and it changes those types of energy into electrical energy. So how would it do this? Well, the idea, and we've talked about it before, is if we turn a turbine, we can turn a magnet inside of an electromagnet, and we can generate electricity through electromagnetic induction. When we do that, and we can turn the turbine in a number of different ways, using falling water, by using other sources of energy to heat water to turn it into steam, and turning those turbines with steam. Once those turbines are turned, they can be turned by wind as well. We can then generate electricity, and through that generation, through the electromagnetic induction that we generate that electricity, we can then transport that electricity over large distances to be used at other places. So its construction is actually the same as an electric motor, but the function is the opposite. And I've kind of mentioned that. So let's move on to copying this page down here. So it's a device that transforms other forms of energy into electrical energy. Construction is identical to an electric motor. The main components are a coil of wire, armature, external magnets, brushes, slip rings for AC, or a split ring commutator for DC. So to explain the operation of AC and DC generators, a single loop coil being forced to rotate clockwise will be used. So we'll just look at this from a single loop perspective. So here's our single loop. We have the current going in one direction on one side and another direction on the other side. We have a force on the conductor from an external source of energy that's moving that, say clockwise, for example. And because it's moving through a magnetic field, we now have a current being generated through Lenz's law. So in the diagram, the right part of the loop is being forced downward by an external source. Using a similar analysis, the induced magnetic field on the conductor must be counterclockwise, and the current must be flowing out of the page. So here we show an entire loop, and the directions that it moves are shown. The current will be induced in the direction shown. An AC generator uses a single loop as well, but it has, instead of a split ring commutator, we use what's called a slip ring. And what happens here, we still have the physical motion of the loop occurring from the whatever source we have, the turbine or whatever moving it. Let's copy this down first. So it produces alternating current. Similar design in the DC motor, except the ends of the loops are connected to two different slip rings. So let's see how these slip rings work. When we look at the armature connected to the slip rings being forced to spin clockwise by an external source of energy. So that armature is spinning. Eventually we lose contact with the slip ring, and it makes contact with the other, which changes the direction of the current flow. So here, in the shaded part here, A rather, the armature is a south pole, and it remains a south pole. At B, it starts to oppose the motion and slows it, and then the current flows in that one direction only. Now it starts to change. At C, it becomes a north pole, and it remains a north pole until point D. So here we've split into a different direction. It's a north pole until here, when it starts to oppose the motion, then we have it change again, change direction, which has it become a south pole, so we have motion again. And then at E, it switches again. So each time it hits these points, these critical points, it's switching from north to south pole, which keeps it constantly moving. The maximum current is induced when the armature is perpendicular to the magnetic field. That's at B and D. So those are the maximums. If the slip rings of an AC generator are replaced by a split ring commutator, the generator is simply able to produce direct current because it's just one circuit being closed each time. The slip rings, they prevent the current from changing direction in the external circuit as it does in the AC generator. But with these slip rings, we want them to change the direction, because AC generation, we'll learn with AC, we can actually transport that energy a lot farther than DC electricity. So a DC generator is designed like a DC motor, but it produces a direct current. Essentially, it's the same idea, but we're rotating the coil of wire, and it's making contact with our split ring commutator. The output graph would basically be like this, where we generate electricity until we hit a point of maximum. That's when we start to oppose the motion, so we have to change the direction. And we keep having these humps which show our electricity generation. Let's move on here. You can read that for more information. So in order to make a generator economically viable, it must be able to produce as much electrical energy as possible in the most efficient way. So we can increase the number of coils. Sometimes we call those windings. We can use a soft iron core in the center. We can keep the relative motion as high as possible, and we can make the external magnet as strong as possible. So here are some ways to improve our electric generator. Electric generators used in power plants contain multiple coils and armatures. The field magnets are not permanent magnets because it's difficult to make a strong enough magnet. Also, permanent magnets lose their magnetism over time because of the strong magnetic fields in the coil. Instead, electromagnets are used. The current needed to power the electromagnets comes from the generator itself or from another generator.